So at a distance, what is the radius of this? Let it be r. What is the length of the cylinder? Let it be x. Linear charge density of this be lambda. It's a positively charged dot. I want the field strength at a distance r. We know lambda by 2 pi epsilon naught r. But to get that answer, how much we have struggled? Can you remember? Did we got that answer very easily? The answer is no. So first we should assume a small element, then we have to calculate the field, then we should define the limits, then integration, then again we'll get the vector one, then again putting the limits we got. In a very simplified way, we are going to bring the answer now. What is the thing? Sir, why you assume Gaussian cylinder? We know electric field due to line charge, it will be radially outward. The electric field due to line charge is a radially outward field. I'll assume one more here. Anyway, one surface enough, and there's a small elemental surface. This is n cap. This is a ds. Then d phi is equal to phi flux is equal to E bar dot ds bar. Now, what is the flux equal to? Net charge enclosed by the Gaussian cylinder by integral of E bar dot ds. So shall we write this as E ds cos 0 degree? You check at all points, the E bar will be parallel to n cap, and E is constant at a distance r. What about flux by this? This will be 0. Because here n cap will be like this E bar. So flux by this flat faces or circular faces will be 0. Only lateral face will contribute. Then this will be, what is the net charge enclosed? Lambda into L. E is constant at all points. So integral of ds. What is integral of ds? Area of lateral surface. It should be equal to 2 pi RL. Very easier one, no? Only thing is you should be very good in this Gauss law. That's all. So like I didn't like this so Gaussian cylinder. I'll go for spherical one only. Okay, let's see what happened to that student. There's no rule, no, that you must. Okay, student, no, sir, like, let me try with spherical one. Okay, let's see what will happen to the student. It's a Gaussian cylinder, Gaussian sphere. Let's see that. So what is the radius of cylinder? Let it be R. Here I'll assume a surface, and let this be the. Look at different points. how E bar due to anywhere E bar should be. I'll show it only at 3 places. Look at n cap. N cap should be radially outward. So here E1, E2, E3. So what is this? Gaussian sphere. There's a point charge. Also, there's a line charge. What is the problem? So what he has assumed? He has assumed a Gaussian surface. Will he get answer? Will he end up with answer? No. The RHS, how it will be? The RHS will be E1 ds1 cos theta 1. So can anybody solve? Not possible. So therefore, like a what shape you like, you are going to assume a Gaussian surface, or you are going to follow certain rules, the rule 1 and 2. You have to assume a Gaussian surface in such a way that the E bar should be constant at all points on a Gaussian surface. And also E bar should be parallel to n cap. But sir, here E bar not parallel. Oh, anyway, flux due to that will be 0. So what is the problem here? If you assume a Gaussian sphere, not wrong. Gauss law is not wrong. You'll not get answer. Tell me, like, what becomes very important now? The Gaussian surface. Assuming a suitable Gaussian surface is what you should assume. And you know what are the type of charges we have. We have a charge like point charge, line charge, charges sheet, cylindrical charge, spherical charge. There are 7 or 8 charges are there. So for that 7 or 8 charges, one student, if he knows what is the Gaussian surface, then it's over. Then the headache of assuming suitable Gaussian surface will get over. Fine. So the what is the Gauss law? You can see that we are able to get answer very easily. Very simple. So 2-3 steps, it's over. So it will minimize all the mathematical calculations. Let me similarly start with. Can you remember we have done for a non-conducting charged sheet, the electric field? So here I assumed a Gaussian cylinders here. What are these? Gaussian cylinder. This also. So this is surface delta S, delta S. Here also I'll assume. So how many surfaces are there? 1, 2, 3, and 4. Okay, now thin charge sheet. So there's a plane diagram. There's a plane diagram. The sheet. Oh, sorry, there's a 3D diagram. This will be the diagram, what you can see, that one plane diagram it is. Then we know the electric field will be perpendicular to the surface of a sheet. And this is the E bar vector, this is the n cap. E bar vector, this n cap. These are unit vector. Red color arrows are unit vectors. All will there flux due to the net flux will be flux due to surface 1, 2, 3, and 4. Then flux due to phi 1 what will happen should be E into delta S cos 0 degrees. Yeah, I'm asking you to look at here. E bar parallel to n cap. Fine. The angle between them is 0. So cos 0 degrees. Then similarly, look at here, surface 2, E bar and this n cap. I think the sheet, you know, it will produce field. If you keep a point charge, it will produce field on either side. So same thing with the sheet also. So it will produce field towards left. So E bar and this is n cap. So ES cos 0 degrees. Then what about here surface? E bar will be in this direction. This is the E bar. But n cap is like this. What is the angle between them? Will be 90 degrees. Let me write it here. E bar. Here also this will be E bar. Then E, say delta S dash cos 90 degrees. E delta S dash cos 90 degrees. This surfaces I'll indicate by some other color. So this will be E delta S 0 plus 0. What is the flux? Flux should be equal to net charge enclosed to E delta S. Okay, what is the charge enclosed? You are going to stand here. Then you are going to see through this cylinder. Then this much of charge is enclosed by the cylinder. Am I right? What about this cylinder? There is no charge because there's a non-conducting charge sheet. Will I have charge only on one face? No charge here. So what is the charge enclosed by this cylinder? 0. Charge enclosed by this. Sigma into delta S. If you stand here, So what you'll write? Sigma into delta S. So the expression will be sigma into finally what is E is equal to sigma by 2 epsilon naught. And the same expression, how we brought it, it was very lengthy, no? The mathematics. First, we should know due to ring. Then after ring, what we should know due to the electric field due to disk. In the disk, we'll put expression for there are infinity, then we'll get a non-conducting charge sheet. I think this was the rule. Very, very lengthy mathematical procedure is what we applied within 2-3 steps. Provided you must know just a basic idea of the Gauss law. Any doubts you can clarify? Any doubts you can clarify? What do you mean by box, Ma? What do you mean by box? This one, huh? Neha, what do you mean by box? Say this box is a Gaussian surface. Only thing is it will not help you to get the answer. Still you have to call Gaussian surface. Nothing to do with that one. Any surface, if a charge, if any surface encloses a charge, it will become Gaussian surface. You will not get answer, that's all. It's a Gaussian surface still. Gaussian surface need not be of this shape. It can be of any shape. You want answer, assume suitable Gaussian surface. Getting? Just general thinking, nothing to do. Don't think that only if it fetches answer, it's a Gaussian surface. No. Gaussian surface can be of any shape. But we should draw a suitable shape so that to get answer. No, sir, I like this shape very much. Okay, enjoy. You may get, you may not get answer. Provided if conditions are satisfied, if get answer, will not get answer. Fine. Just some logical thinking. That's all you have to understand. This is like a tool. It's not a concept. It's a mathematical. You can select it's a tool, which will really help us a lot to find out the field due to charges systems. Okay, then will you really thank your physics teachers? Thanks for introducing such a great tool. Okay, let's see that. Really, this tool, is it a versatile? Means we can find out for any charges system. Okay, the answer may not be. Okay, there's a ring. Let's do one thing. We'll find out the charge. Total charge, let it be Q. At a distance X on the axis, we have to find out the field strength. We know what is the formula? KQ X by root of R square X square to the power of 3/2. Fine. Look at this one now. I want the field strength. Okay, tell me, like, can you use Gauss law? Please try to think. Okay, then I have another very good question. Line charge, finite line charge, not infinite, finite. Like this, several bodies I'll bring into picture. Hemisphere, solid hemisphere, I want field strength at 0.2. What suitable Gaussian surface you can assume? So what are the conditions for Gaussian surface? E bar should be parallel to n cap and E should be constant at all points on a Gaussian surface. Tell me like what you are going to do in this case. The answer is no. We don't have any suitable Gaussian surface. We can't find EP by using Gauss law. That's all. Finish. Or any reason? Because the Gaussian surface, which will simplify their conditions, not available. Here also same thing. So is it really Gauss law that powerful so that for anybody you can find out? The answer is no. Only for we can't find out EO. What was the problem? Shall we say Gauss law is wrong? No, it's a law, fundamental, like Coulomb's law, how it is also a fundamental. So there's no problem with the Gauss law. There's a problem with the suitable Gaussian surface. Fine. So there's no problem with the Gauss law. What is the problem? Problem with the suitable Gaussian surface we are unable to imagine. Finish all. So nothing to do with the Gauss law. Gauss law is a very fundamental law, like Coulomb's law. So don't question it. Don't say Gauss law is wrong. In all about 3 cases.
For finite line charge, we can take a cylinder now, sir, and take 3 surfaces like we did in the previous.
You know, ma, what is the electric field due to finite cylinder? Try to, for long rod, E bar is like that, no? For finite will not be. I gave one formula, the vector formula. Check it. I cap, J cap. The E bar will be different at different points. Go back line charge. If you have a notes, turn pages. Electric field due to finite line charge. As you vary the point, what happened? The alpha, beta are going to change. Definitely. The E bar will be different at different points. In all about 3 cases, is suitable is not available. Okay, no, so it's not something really. So we thought maybe, okay, fine, okay, Gauss law is there, so I need not to bother about integration. It's having its own limitations. For symmetrically distributed charges system, the Gauss law really going to help us a lot. Anyway, we are not bothered. Actually, to be frank, I'm bothered about the conductors. I want to find out field due to conductors. That's what the Gauss law is going to help us a lot. What is there in this? Very simple. Already this you have done in gravitation, no? Look at once. What is there in calculation? 90 degrees here. So flux due to this surface will be 0, due to this will be 0. These two will add up flux. Then charge is enclosed only by this cylinder, E into delta S. There's no charge here. So what is the charge enclosed by this cylinder? Will be 0. So if you want to write that instruction, charge is Gaussian cylinder, encloses charge. It's like a revision. We have done all this in gravitation chapter. So it's not some first time you are seeing these things. Huh? So you should recollect. That's why I told you long back, no, revise once.